the voicemail.
Yeah, slightly wondering whether I'm in the wrong workshop, because there were 3 talks this morning about algebraic effects in the Poke workshop. There is some. Okay. Yeah, so this work is about extending or adapting work on algebraic effects and handlers to a set of idioms and arrows, which are other notions of computation, rather like maths, with certain restrictions. So I'll start off by giving you the idea, which will make more sense as I sort of go on. So algebraic effects, which were introduced by Gordon Hopkin and John Power, give a way of describing computations abstractly. They're very closely related to monads, but the algebraic approach gives a different take. Has some advantages. So in this setting, we can view abstract computations as being just trees that describe the progress of computation. And then in the conventional setting, all the previous work on algebraic effects, these trees are monadic in some sense. And the key idea of this work is by restricting the form of these trees, first by making control flow static, we get arrows, and if we restrict them further, then we get idioms, so that the data flow is also static. And what I did was I enforced these restrictions in a type system by adding some special effect computations, some flow effects. And then in this setting, once you define your abstract computations, which we can view as trees, the way we actually implement some kind of behavior is what's called a handler that you can see as an interpretation of one of these trees. So it's like defining, it's analogous to giving you a definition of a monad. We can write lots of monadic programs, but then we can interpret those programs in different monads. And yeah, so I've generalized handlers to arrows and idioms as well. Okay, so yeah, now I'll give you some background to show you where the inspiration for this comes from. So monads were introduced by Mochi, and I'm sure most of you know about monads. And then arrows are a restricted version, a more restricted kind of effect for computation that John Hughes introduced. Which turns out to be useful for various things. I mean, partly it sometimes gives you more efficient implementations, and then there are some things that are arrows that are monads, which is more general. And there are lots of practical reasons why you want to use these things. And then idioms are even more restricted. It's used by Oliver Bryant and Patterson. And then going along a different dimension, we have the algebraic approach to effects by property power and handlers for algebraic effects. And at last year's, another inspiration is this call by push value calculus. And then this work is kind of combining 2 strands of work that I did previously. One was idioms or oblivious arrows and monads and promiscuous, where we looked at the relationship in expressiveness between these different notions. And then handlers in action, which is a calculus for algebraic effects and handlers. So yeah, in effect I brought these 2 things together. Anyway, in this talk I'm not going to sort of go to much technical detail at all. I'm going to try and be very high level. And primarily I'm going to be talking about trees. pictures of trees. So let's see, this is the key notion I'm going to start off with. So an abstract computation over an effect signature with a return type A is a tree. So this effect signature consists of a number of operations that have inputs and output types. And then computation finally will return a value type A. So nodes in these trees are labelled with the operations, and the operations can have parameters. The edges are labelled with the result values of running the operations, and then the leaves will be labelled with the final return values. So here's my first very simple example. An effect signature with two operations, get, which we can think of as just reading from a single Boolean state cell, and B, which, well, maybe just B. This is an abstract computation, so we haven't said what these things mean. This computation, noisy, what does it do? It gets a Boolean. If it's true, it just returns true. If it's false, then it beeps, and then returns false. Pretty simple. Yeah, so the things in red are the parameters, the things in blue are the return values of the operations. Another very simple example. Now we have read-write states, so we have a put operation as well, but the input is Boolean and it doesn't return anything. So yeah, define a flip operation. What does this do? It reads from reads value, and then if it gets true, then it writes false. If it gets false, it writes true, and it returns the original value. Another variation, a reset. It's just like flip, except it always writes false. Okay, you might wonder why I define these very simple examples, but first of all, yeah, these computation trees they describe sequential computation, and really, so fundamentally that's what abstract effectful programs are about. It may be that some particular interpretation of some effectful program might be parallel or something, but the programs we're writing capture what it is to be sequential. The descendants of a node in general can depend on the result value you get. So, I mean, that's clear in this case. The left branch after the get is in a different shape to the right branch. And we identify three different kinds of dependencies. So the control flow dependency says that the actual operations that get performed can depend on previous results. A data flow dependency is where the parameters depend on the prior results. So like in this case, even though we always get a put here, the parameters put can change. The branches of this branch is false and this branch is true. Whereas actually in this one, there's no data flow dependency or control flow dependency. And then the other kind of dependency we have is the final return values depend on the prior results, they call that memory dependency. So, in this previous work that I did with Phil Wadler and Jeremy Gallup, with this title Idioms are oblivious, ours are meticulous, monads are promiscuous, we looked into the relative expressiveness of idioms, ours, and monads, and we did give an informal characterization in terms of control flow data flow. We didn't bother mentioning memory because that's always dynamic. And the intuition is that idioms are computations in which control flow and data flow are always static. So you can never have any dependencies in your abstract idiom computation, except that only the final results that you get can depend on the results of prior computations. And then with so arrows are meticulous in the sense that we can have some. The control flow is not allowed to be dynamic, but the data flow may be dynamic. It can meticulously distinguish between the two, and that becomes apparent when you look at the formalization. We introduced this arrow calculus, which partitions the context into two parts. Whereas monads are promiscuous, they can just depend on anything. Oh yeah, no, I should address this. Why do we care about these static computations? Why don't we just sort of allow completely unrestricted trees? So one reason is that we can actually give different interpretations to our effective computations. If we restrict things, then that opens up new possibilities. There are some things that are some functors that are idioms, but are not monads, for instance. And the same for arrows. Also, by restricting things, it allows us to do lower level implementations. So arrows correspond quite closely to circuits, for instance. And then optimization is another thing. By being more static, it's hardly surprising that that opens up new opportunities for optimization. So now I'm going to go back to my examples. The first one is a monad tree. In that it has both the control flow and the data flow are dynamic. So yeah, what I'm doing for each of these is decomposing them into control flow, data flow, and memory trees. So you can see that all these things are trees. Whereas the flip example is an example of arrow computation. If you look at the control flow tree, you see that these two parts are identical. But we don't really need to represent that as a tree at all. It's just a list. It's static. But we can't do anything with data flow. The reset example, again, we can collapse the control flow into a list and also the data flow. Okay. So yeah, so far I've just shown you some trees. Now I'll give you some indication of how you can actually program with these things. So here I'm kind of using basically a strict, a call by value language with effects. So the noisy example, the type of it we give this, which says that it's the braces indicate that this is a suspended computation, and the signature there is an effect validation. So it says that this computation may perform getting the effects. And then this is probably hopefully a very obvious and natural way of writing this computation. Read from the cell, and then if it's true, then you just return it. Otherwise, you beep and then return it. And then similarly for flip and reset. Okay, there's probably nothing particularly unusual there. So a key contribution of this work was adding these control flow effects. So I have two of these. One of them is the dynamic flow effects. One is for dynamic control flow. If we have a C present in the effects, that says that it's allowed to do dynamic control flow. And then D is for data flow. So the first example, the monadic one, has both the C and D effects. The second one has if it's monadic, the second one has D effects. And the last one has none. That's an idiom computation. the syntax for these things is completely beautiful. We can also, of course, this one, we could give the C effect if we want. We just don't happen to use that as a control point. And similarly, this one could have the C order correct. But contrast this with how we would write these examples in Haskell. So in Haskell, there's a do notation that we can use to write some monadic code. But we don't write arrow code in the same way with the kind of do notation. We have to write something like this. And then for writing, if we want to do an idiom one, then we have to write something like this. Also, note that we can't use the same get and put operations. We can find different ones. So yeah, I mean that's probably the key advantage of my system is that we can write generic effectful programs using a single syntax, and it's the flow effects that allow us to move between idioms, arrows, and monads. I probably didn't even say that. I should have said that earlier. But I'm using idiom. The Haskell people like to use the word equivalent functor, but Connor's original word was idiom. I like it. I haven't talked at all about effect handlers. I'm not going to. I don't have time to give you all the details, so you need to look at the paper for that. But I'll try and give an intuition for what handlers are. So, like I said before, we can view a handler as an interpreter for an abstract computation. And the way it's defined is as a fold over a computation tree. So like pattern matching basically. So you'll have a case for what to do with the return value, and then for each kind of operation, also how you handle that operation. And it's a little bit involved because you actually have access to continuation as well, do interesting things with continuation over it. So I'm not going to give you any implementation of handlers, but I'll give you some examples of how you might use them. So supposing the state, yeah, so here's an example of monadic handlers. I'm going to give you two examples of monadic handlers for state. The first one is a valid state, like the Haskell valid state function. It will take a stateful computation, returns an A, and it will interpret it as a function from state. Okay. So this isn't like the state monad, is it? It doesn't actually return the final state, but we could do that as well. And then we could have another interpretation. We call this log state, which does return, as well as the final value, it returns a list of, say, all of the intermediate, all of the states that the computation held. So if we, for instance, run a val state on reset with true, well, we'll just get that true because it throws away the state. If we run log state on resets, then you get back true, and you get initially the state is true, and you get such false. And you can have as many of these interpretations as you like, as many handlers as you like. And they compose in nice ways, but that's kind of not the subject of this talk. And one of the technical difficulties of this work was working out how to adapt handlers to the arrow and idiom setting. I'll just give some more examples, and some slightly contrived examples, or very contrived examples of handlers, arrow handlers that are not monad handlers. Because given any monad handler, we can always automatically generate the equivalent arrow handler. Because if you about these things as just interpreting trees, all it's saying is, well, if we can interpret all trees, then certainly we can interpret them restricted. So given the eval state one, we can generate an eval state handle for arrows. A key difference is that the input to one of these handlers is actually parameterized by the context. And the point is that with monads, when you compose computations together, you do that by using continuations. And a continuation in the monad setting is always just a quasi-arrow. It's a function of type A to T of B. Is the monad constructor. But arrows, it could be some completely different function space. So that's not possible in general. So yeah, you kind of have to thread the context through the computation as you go along, and that's what the technical parameter is here. And that also appears here. Anyway, yeah, the prime example of a handler is this one, puts, which doesn't actually, the idea is it doesn't actually run the computation. It just statically determines whether it does any writing at all. And if you think about it, you can't possibly do that for a monadic computation because that whether or not it does writing may depend on the results of some of the behavior. Whereas in this case, in the arrow case, because the control flow is static, we can do that. And then, yeah, so I'm just passing in an empty context here, basically, in the eval state, and then it behaves the same way, and then puts, if we run that on this reset example, it does do some writing, so that's true. And then idiom handlers are similar. Again, you have to, it turns out you have to sort of thread the context through for the same reason. So again, you can translate eval state, and you can also translate puts to an idiom handler kind of thing. But then an extra, we can also write other handlers that there's an arrow handler. So the idea of list puts is this is going to, it's a bit like the logging one again, except it's not going to actually feed any state through at all, but we can actually statically determine all of the parameters that are ever going to be passed to the put operation. Which, I mean, if we look at that tree, it's clear that we can statically determine this because it's always the same. It's just going to be false. Okay. So there's a load of other stuff in the paper. All the details of the formalization of this. The key thing you need in order to be able to enforce the flow constraints is that the environment is partitioned into the things that you can definitely access and things that you're not necessarily allowed to depend on. So it's a bit like the substructural type system. And then I've got an example involving parser combinators, which I think gives quite a nice intuition for why this kind of thing might be useful. So you can see that we can write our parsers using the same constructs, even if they're idiom, arrow, or monadic ones. Idiom ones are give you context-free grammars, the arrow parsers give you a limited amount of context sensitivity, and the monadic ones give you full context sensitivity, which is pretty sharp. That's sort of some future working stuff. But I'm going to, I'll stop here.
Okay. Let's thank Sam. Great. So I thought I'd say a few words and ask a couple of questions. So my view on all of this and the history behind effects and monads and handlers is that with monads, what we kind of traditionally do is sit down and think about how we're going to encode effects. We write some data type, and then we go and think about the operations that can fit the monad pattern and fit the data type. But this leads us to all these problems with compositionality, which is a really nice thing about effect handlers. You get this great flexibility by starting with the operations, thinking about what effectful things do I want to do, and then getting this encoding via the free monad construction later. So then I suppose a natural question which has been in my mind actually for many years is, well, what's the analogue for other notions of computation, other classes of computation that we can structure in other ways, so idioms, arrows, comonads, etc. So Sam's done something really nice here by answering that question and coming up with, I think, a very neat way of putting this together and having this distinction between things that are static in their control flow and things that are static in their data flow, and using this distinction to put everything together. So I think what's really interesting about the work is that once you get the calculus, this lambda flow calculus, you're not thinking about monads or idioms or arrows, you're just thinking about what's the control flow, what's the data flow of my computation here. All of this other maths stuff has just dropped out, which I think is actually quite a nice result and very interesting. So I think the flow effects really reminds me of just classical liveness kind of analysis and other data flow, control flow analysis and compilers. So I wondered to what extent it's possible to sort of infer these things. If you just write the code without any signatures, can that be inferred for the user?
It could be, yes.
Yeah.
Often the user knows what they're trying to do anyway.
Yeah.
Yeah.
But the nice thing with the types and the signatures is that you can give a programming interface to say, well, this computation accepts a structure which doesn't have dynamic control flow or something like this. So, yeah.
I'm not sure if you end up with nice sort of principal typing properties.
Yeah, maybe you need to give some hints. But it does remind me of the things that have been done for Wali compilers, looking at the control flow and the data flow. Okay, well, I won't ask more of my questions. I'll open it up to the floor so that we can get some audience questions.
Yeah, so you talked about this nice single syntax for idioms and monads and arrows and so on. But then, talking about syntax, you were using this set notation and subscripts and braces. And what's the status of this stuff? Is there only theory or some implementation somewhere?
There's only theory at the moment.
Okay, because I always get a bit suspicious when there are unions and C and B, and it's very easily creeps in features which, when you turn out to want to implement them, you've sort of used mathematics as a meta language there somewhere.
So I've actually the formalism is built on call by push value, which I guess the key important feature that has, that I think you probably do want in the implementation of this as well, is a distinction between suspended computations and functions of type unit to a, it has sort of a first-class representation of computations as values. But yeah, I think.
We have, for example, the state S, which is sort of a definition of a set of an effect system or something like that, and then it was used state S and then plus union something else. And I mean, it's not clear what the language that you can write those definitions.
There are plenty of implementations of systems with effect handlers and algebraic effects. So if you throw away all the flow effect stuff, all of this stuff has been done in practice, and it's well understood. I don't think there's anything sort of suspicious about it. The only thing that you might be suspicious of is adding the flow effects.
Well, and it's syntax. Yeah, we can come up with some nice syntax at some point, but I guess
but
that's
yeah,
outside the scope of Sam's paper. Okay, question.
No, actually, related to what he said, there are some efforts in the ASCII community to have a do notation for applicative.
Yeah, exactly.
And I wonder if you could latch onto that work, because that would be really, really useful.
Where's Thomas in the room?
He's down in the corner. No, he's just there.
All right.
Yeah, that would be, I think.
But F sharp has that.
Yeah, of everything. Yeah.
Well, not for completely everything, but
Always.
we combined the idioms and monads. We don't know how to add some other things like arrows into the same unified syntax, but idioms and monads work nicely together.
Yeah. I mean, in a sense, the natural syntax for idioms is just we have this n-ary
Yeah, but I think
construct.
people care much less about idioms. Like I think applicative in Haskell would be a big advancement. You could just write good notation.
Yeah, and there is this active work being done, I think, by Sam Marlowe at Facebook.
Yeah.
And they're actually making do notation the sugar into applicatives when it's possible, when the control flow allows it.
We also, in the links programming language that I worked on with Phil Wadler, we have a specific instance of an idiom notation like that, kind of combined with it's combined with XML in an interesting way, but it has the same kind of n-ary let binding thing with the F sharp.
But even in Haskell, there's this sort of list comprehension, generalized list comprehension syntax.
That's different though because that's still an applicative notation rather than a.
Yeah, but it has some of it, but again, like in another way that doesn't quite fit in the same model.
Let's just have a quick last question for Oleg then.
Well, first of all, it's a remark about your your remark is that,
Yeah.
well, yes, I mean, I know it's if you talk about free monad, it's always all nice, I mean, until you get to interactions, right? So that's the key is how you interact effects and if you effects interact, right? If you only deal with state and writer, then there is nothing interesting happens. So then, of course, you can say, oh yeah, everything is easy.
Yeah.
So things are not that easy when you add some interesting control effect, especially to control effect. And I mean, my question is, it's actually, Patrick already asked a kind of, I'm not sure that unifying applicative and monads is that, well, you kind of made a swipe on Haskell, oh yeah, there is kind of do notation one things and applicative another, but they actually express interesting things, right? In do notation, you actually have data flow, you have bind, right? And it's actually syntactic, enforced, and applicative it isn't, right? So it's again syntactic restriction. So it's actually quite nice when you enforce certain things using syntax. And using types, and then it requires a lot of interesting things about bound variables, right? So I'm not, which variables bound and where you put it in an environment that take again. So, so first of all, I'm not sure that what you propose unification is going to, give us any gain. In terms of conceptual or maybe in terms of even implementation, because in Haskell implementation is actually nice, it maps to
Well, I think this is conceptually much simpler. But
well, no, look, unification, I'm not saying that that unification of monadic and applicatives, in a single notation would be conceptually any useful thing to do. So I'm not sure about it because the bind enforces the syntactic restriction of the data type, and syntactic when something is enforced syntactically is always nicer when it's enforced in any other way because it cannot even screw up, right? And also, also leads itself to better implementation.
What I would say is that it depends on what your particular application is. If you're trying to do something, implement something very applicative, then it's very natural to use an applicative functor.
Yeah, but
sometimes, and to use that syntax, but sometimes you find yourself wanting to do lots and lots of bindings, and that's a real pain because you end up having this. Well, like if you use a power combinator library with applicative functors, you end up with this lambda that binds a whole load of names, and then you have this list of names, and you have to keep track of the order. That's painful.
Well, let's take the flight offline. Thank you.